Alright, Physics 2212 Lab 5. Introduction. Purpose of this lab was to observe Faraday's and Lenz's law with a bar magnet and an aluminum foil roll. Assumptions we made in this lab: we ignored air resistance and we only accounted for gravitational and magnetic force. System and surrounding system for this lab was the magnet and the foil roll. Surroundings was everything else. Main results from this lab: so the experimental time for the magnet to exit, the one we did in real life, was 1.098 seconds. And the computer time in GloScript was 1.014 seconds. Initial conditions: the magnet is dropped from rest into the foil roll. Moving on to concepts and principles used in this lab. So concepts include Faraday's law, Lenz's law, which are defined right there, Biot-Savart law, which is also given below, Newton's second law, which is F equals ma, the time derivative of magnetic flux of a dipole, which is in this picture right here, and the magnetic force on a loop, which is given right below it. Majority of these are going to be used in the GloScript. Procedure for the lab: when we did in real life, we noted the north side of the magnet using a magnetometer app, and then we dropped the magnet down the aluminum foil roll and recorded the time it took for the magnet to exit. And then we did that 5 times and recorded the average. These are the runs we did, and the average right here, 1.098. And these are measurements of our aluminum foil roll right here that we use in GloScript as well, and magnet measurements right here, 0.023 kilograms. Checkpoint questions that were in the lab document. Why can't we use a ferrous tube, for example, steel pipe? A ferrous tube would distort the magnetic field of the falling magnet. Steel, being ferrous, would create its own magnetic field in response to the magnet and alter our measurements. What happens to the magnet? How does this compare to a magnet falling in free space without a tube? A magnet would fall faster in free space as there's no magnetic force due to the induced current that is acting opposite of gravity. GloScript code. We will go over that right now. So here's our GloScript code. And starting from the top, we added in our measurements that I went over before, and our mass and mu mag as well. 0.979 is what I had from lab 3. This was the corrected value. And moving on, we added a dipole B function. We added a dflux dt analytic function. And in the simulation loop, we used those functions to calculate the B field and add it and make sure the simulation went according to plan. Here we have Fnet as well, and then here we have Newton's second law to find the magnet's velocity and position. And running this program, we can see this right here. There's our tube and magnet, and here's the graph that we have and the time that I mentioned before. And we'll go back to the PowerPoint. Okay. Similarities and differences between our GloScript and real life. The computer time, the GloScript time, is less than experimental time, and this may be due to the simulation being in ideal conditions. Sources of errors for also why they could have deviated will be explored in a couple of slides, and overall the times were pretty close to each other, unlike my previous labs, so it's always a plus. Interpreting the simulation. So right here, the first graph is using my mu value from lab 3, and this was the corrected value down below. And the questions: the intensity of the coloring of the tube indicates the magnitude of current flowing through each ring. Red and blue indicates current flowing in opposite directions. Which color corresponds to clockwise and which one counterclockwise, and how do we know? So red was counterclockwise and blue was clockwise, and we know this using Lenz's law. What happens to the dynamics of the system when you flip the magnet around? So flipping it around would invert the direction of the induced currents. The dynamics should stay pretty same. How does the total time in tube of your real-world system compare to that of your computational system? How might the computational system be made more accurate? So as mentioned before, the computer time was less than the real time. The computer system can be made more accurate by accounting for the assumptions that we made earlier, and also my mu value needs to be recalculated. I did not mean to move on. What does the shape of the velocity versus time plot tell you about the forces acting? So when the plot has a constant velocity, as can be seen in the middle right here, it means that the forces are equal and opposite, and there's no acceleration happening. Sources of error. So some of the sources of error stem from our assumptions, when we ignored air resistance and other forces. There's also human error in recording the time for the real measurements, and also mentioned many times the incorrect mu value from lab 3. What if and what if? So what if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The induced current would be of greater magnitude, and we know this with Ohm's law. This would cause the magnetic force to be much greater, as well as causing the magnet to hover. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? So cutting holes or slots would interrupt the path of the induced ring currents, and this would cause the magnetic force to be of less magnitude, and the magnet would fall faster through the tube. And that's it. Thank you.